If a charged particle moves through a region which have both an electric and a magnetic field, it can be affected by both an electric force and magnetic force. If these fields, electric field and magnetic field, are perpendicular to each other, we say these are cross fields. If the forces are in opposite direction, a particular speed will result in no deflection of the particles. So let's discuss few cases of cross fields. This is a velocity selector. A beam of charged particles is produced by a heated cathode or maybe by using some radioactive elements. Not all the particles move with the same speed. So particles of some specific speed are selected here and from the beam using an arrangement of electric and magnetic field, and this arrangement is a velocity selector. So a charged particle of mass m, charge q and speed v enters a region of space where the electric and magnetic field are perpendicular to the particle's velocity, and they are also perpendicular to each other. The electric field is to the left and the magnetic field is into the plane of the figure. If charge is positive, the electric force is to the left with magnitude QE, and the magnetic field is into the plane of the figure. And magnetic force is to the right, and the magnitude of the force would be QVB. So for these E and B, if electric field and magnetic field magnitudes are given, then for a particular value of speed V, the electric and magnetic forces will become equal in magnitude, and in that case the force becomes zero and the particle travels in a straight line with constant velocity. So in such a case, the total force becomes zero, and it shows that there is no deflection, and the speed of the particle is the ratio of electric and magnetic field. Only the particles with speeds equal to E over B can pass through without the deflection. This one. So by adjusting E and B appropriately, we can select particles having a particular speed for use in some other experiment with the help of such type of setups. And the velocity selector also works for negative charge particles, and it is also working for positive charge particles. So one of the landmark experiments in physics, which was performed by J.J. Thomson in 1897, was to measure the ratio of the charge to mass for the electron. Thomson used this apparatus, something like that. My drawing is not very good, you can consult a book for the very accurate figure. And here this is a highly evacuated glass container. Electrons from the hot cathode are accelerated and form into a beam by a potential difference V between the anodes and A dash. The speed of the electron is determined by the accelerating potential. The kinetic energy equals the loss of electric potential energy. We knew this from the previous knowledge, and we can write it. Yes. And from here, the speed of the particle. E is the magnitude of the electron charge, and the electron passes between the plates P and P dash here and strike the screen at the end here of the tube, which is coated with some fluorescence material, and it glows when the electrons fall on the screen. The electron passes straight through the plates, and also at the time a magnetic field is also present there, and this is the condition where uh, V is equal to E over B, a condition of cross field. So we can write E over B equation into this form, and from here E by M ratio becomes so all the quantities on the right side can be measured. So the ratio E by M of charge to mass can be determined, and it is also not possible to measure E or M separately by using this method, only their ratios. And the significant aspect of Thomson experiment was that he found a single value for this quantity. It didn't depend on the cathode material or the residual gas in the tube or anything else about the experiment. So this independence showed that particles in the beam, which we now call electrons, are a common constituent of the matter. And this lead to the discovery of the first subatomic particle, which is electron. And he also found that the speed of the electrons in the beam was about 1/10 the speed of light, much greater than any previously measured speed of a material particle. So the most precise value of the E by M is 1.75882012 15 to the rest of all 11 coulomb per kg. And after 15 years of Thomas experiment, Robert Millikan succeeded in measuring the charge of the electron very precisely, and this value together with the value of E by M, the value of the charge, enable us to determine the mass of the electron. So the most precise value available at present is for the mass of the electron is 9.1 1.109 382616 into 10 raised to power minus 31 kg. So similar to this Thomson's E by M experiment, some techniques can be used to measure masses of the ions, and then atomic and molecular masses can also be measured. So in 1919, Francis Austin, a student of Thomson, built the first of a family of instruments called mass spectrometers. And here a positive ions from a source pass through the slits S1 and S2, forming a narrow beam, and these ions pass through a velocity selector and with crossed E and magnetic fields, as we already discussed in previous cases. And then when they are passing through the cross field, as we already discussed, all ions will be blocked except those with moving with speeds equal to E over B. So finally the ions pass into a region with a magnetic field perpendicular to the figure, and the ions here in this magnetic field they move in circular arcs with different radius or radius with different radiuses, and radius can be measured by using QB dash. So here at the end there is a photographic plates which give information where the massive ions are hitting the detector, and in this way particle masses and radius can be measured, and with the help of this formula. So one of the earliest results from this work was the discovery of neon that has two species of atom with atomic masses 20 and 20 gram per mole, and from this discovery we came to know about the isotopes of the elements. So let's do a very simple sample problem which is related to the E by M experiment. Here you set out to reproduce Thomas experiment with an accelerating potential difference of 150 volt and a deflecting electric field of magnitude 6 into 10 raised by 6 Newton per Coulomb. And what we are interested to calculate the fraction of the speed of light do the electrons move, what magnitude of the magnetic field we need for this, and with this magnetic field what will happen to the electron beam if the accelerating potential increases by 150 volts. So we know that to determine the speed of the electron we will use the equation V is equal to 2 E by M into V. So from where this equation came, this is V is equal to 2 E over 1. When we equate kinetic energy equal to electric potential inertia. So just put the values here, and the speed we obtained would be 27.27 into 10 raised by 6 meter per second. I just did this step directly, but I will do it to 1.76 into 10 raised by 11 coulomb per kg into 150 volts. So this lead to this speed, and so in order to find the fraction of the speed of light, how the electron move, we divided it with the speed of light. So this becomes 7.27 into 10 raised to power 6 meter per second divided by this gives us 24, which is 2.4% of the speed of light. So the electrons are traveling at 2.4% of the speed of light. So the second part is what magnitude of the magnetic field will you need? Now for this, B is equal to E over B. V is equal to E over B. So we use this relation, and it's 0.83 Tesla is required. So from the previous discussion of this CRT, we know that increasing the accelerating potential increases the electron speed. So it does not change the upward electric force, but it increases the downward magnetic force, which was EVB. So therefore the electron beam will be bent downward, and it will hit the end of the tube below the undeflected position.